Hello students, welcome to the fourth episode of our video example series for Circuits 1 here at NDSU. In this episode, we're going to focus on some circuit intuition techniques as well as a quick example of how dependent sources work within a circuit. Here we have a current source of 6 milliamps, a voltage designated V1 across a 2K ohm resistor, a dependent voltage source designated V1 over 2, and a current I.O. flowing through a 2K ohm resistor in series with a 6K ohm resistor. There is a quirk in the circuit that I left out on purpose. It's this strange little wire right here, connecting the two parts of this circuit. Let's call this part 1, and this part 2. The two parts are clearly connected, but the question is, how are they affecting one another? And to demonstrate this, we're going to try to trace the path of current flow through this circuit. We're going to start at the current source right up here. This is kind of a hypothetical, but just bear with me, it'll make sense. Start at the 6 milliamp current source and flow through the 2K ohm resistor, through that strange little segment of wire, up through the dependent voltage source, then following the path of I.O. through the 2K ohm resistor and the 6K ohm resistor, and then back along towards that strange little wire. You can see that as we drew our line, that strange little segment has current going in the right direction and the left direction. Our intuition tells us that shouldn't be possible. That shouldn't be the case. That's not what's happening in the circuit. And it turns out you're right. If we were to draw a closed loop from one part of the circuit to the other, either or, we're going to find that that single segment of wire connecting them together is going to have two currents flowing in the opposite direction. That's not possible. So we consider that that segment actually has no current in it, since you cannot form a closed loop between both of these parts of the circuit. Okay, so that makes the two parts of the circuit actually electrically isolated from one another. The trick now is going to be what's going on with this dependent source. It's designated V1 over 2. Since we know that the two parts are isolated, solving for V1 is actually rather easy now. V1 can be solved using Ohm's law. It's going to be 6 milliamps times 2K ohms will give us 12 volts. Easy, right? Our designation for the dependent source is V1 over 2. That's going to be 12 volts over 2. That dependent source is supplying 6 volts to part 2 of the circuit on the right side there. Okay, so we know the voltage of that dependent source. Solving for I.O. is rather easy. All we have to do is KVL. Let's do that. 0 is going to be equal to, let's start at this node right here. The first thing we're going to meet is a negative on that dependent voltage source, so negative 6 volts plus 2K ohms multiplied by I.O. plus 6K ohms multiplied by I.O. as well. That'll simplify to 6 volts is equal to 8K ohms times I.O. I.O. is going to be 6 volts divided by 8K. That is going to give us 750 microamps. Excellent. Now, let's check our answers. We're going to do that using power. Let's do some power calculations. The power delivered must equal the power absorbed. Since these two parts of the circuit are electrically isolated, let's calculate the power delivered by the current source as well as the dependent voltage source. Since we know that our resistors are only going to absorb power, the current and voltage source are going to be the ones that deliver power. So the power at the 6 milliamp current source is going to be 6 milliamps times V1, which we determined to be 12 volts. That's going to give us 72 milliwatts. The power delivered by our dependent source, dependent voltage source I should say, is going to be 6 volts times I0, which we determined to be 750 microamps. That's going to give us, let's see here, 4.5 milliwatts. Excellent. Okay, let's do the power absorbed by our resistors. The power absorbed, let's do the 2K resistor here. Let's call that P2K1. 2K1 is going to be equal the voltage across it times the current through it, which is V1 12 times 6 milliamps. It's going to give us the same thing that we got for the power delivered by the current source, 72 milliwatts. The power delivered to the second 2K ohm resistor, let's call it 2K sub 2, is going to be a little different. We're going to showcase some equivalence of power, our power equation. We don't know the voltage across that 2K resistor in this circuit, but we do know the current through it and the value of its resistance. So we're going to use I squared R to solve for that power. And we know what those are. It's going to be I0 squared, 750, whoops, sorry about that. Let's make that right. 750 microamps squared times 2K. That is going to yield 1.125 milliwatts. Awesome. The power dissipated or absorbed in our 6K resistor is then going to be, we're going to use the same equation, I squared R, same current, microamps squared times 6K ohms. That is going to give us 3.375 milliwatts. Okay, let's go back up here. The power delivered should equal the power absorbed. So let's add all of these powers together, the power delivered and all the power absorbed, and set them equal to each other. 72 milliwatts plus 4.5 milliwatts is going to give us 76.5 milliwatts, equal to 72 milliwatts plus 1.125 milliwatts plus 3.375 milliwatts. That is also going to give us 76.5 milliwatts. Our answers match. The power delivered equals the power absorbed. We have solved the circuit. Thanks for watching.